This is lesson 4.1 on one-to-one functions. So in this new unit, we're going to be discussing, we'll talk about inverse functions, exponential functions, and logarithmic functions. In order to get to inverse functions, which is kind of an underlying idea of this whole unit, we need to first discuss one-to-one functions. One-to-one functions, as we're going to see, play a very important role when discussing this idea of inverse functions, which we'll introduce later. If we have a one-to-one function, what that means, so if f is a one-to-one function, that means f of a and f of b. So if we take this function and apply it to two numbers, if the resulting value that we get back from applying that function is the same for those two numbers, that means that the two numbers were actually the same to begin with. What this means is if we think about the graph of this function, the graph of a one-to-one function will not repeat any y values. So if you recall, the graph of a function will not repeat any x values. The graph of a one-to-one function, in addition to not repeating any x values, will also not repeat any y values. So much in the same way that we had the vertical line test to help us determine if the graph of a relation was a function, we have a similar test to determine if the graph of a function is a one-to-one function. So vertical line test, that was the test we used to determine if a given graph represents a function. The horizontal line test is what we will use to determine if a given graph represents a one-to-one function. There are such things as one-to-one relations that are not functions. We're not going to worry about those. We're only going to worry about one-to-one functions. So I want to make that clarification, but calm you to know that we don't have to worry about these several different things floating around. We're really focusing just on functions for this class. So we will only be working with one-to-one functions. The horizontal line test works very similarly to the vertical line test. If we take the graph of a function, if we draw any horizontal line whatsoever, if the graph is a one-to-one function, it will pass through the graph at most once. So if it passes it through it once or doesn't pass through it at all, that's actually perfectly fine. We're going to consider it to be a one-to-one function because that would mean that there are no y values that are repeated. However, if we can draw any horizontal line whatsoever, any at all, as long as there's one horizontal line that passes through the function more than once, so two or more times, that automatically means that it is not a one-to-one function. So, for example, if you recall what the graph of y equals x cubed looks like, the weird little curvy graph, any horizontal line that you draw on that graph is going to pass through it once. There's no way you can draw a horizontal line that passes through it twice or more. Therefore, y equals x cubed, that's going to be a one-to-one function. However, if you think about our parabola, y equals x squared, we can draw several horizontal lines that pass through that graph twice. Two times is more than one time, so that means it is not a one-to-one function. There's some deep math there. 2 is bigger than 1. So y equals x squared is not one-to-one. It is a function, remember, but it is not one-to-one. We're going to take a look at some more slightly complicated graphs, but we're going to use this simple test to determine whether or not these graphs are one-to-one. So our drill problems for this section, extremely simple. We're also going to take a look at a slightly more involved problem where we can determine if a given function is one-to-one without examining its graph. All right, so let's consider these two examples. So these problems, these are the kinds of problems that we will see from this section on our drill quizzes and on the drill portion of the test. These are meant to be quick and simple problems. All we need to do is to use the horizontal line test to check to see if these are one-to-one or not. We do not need to worry about whether or not they're functions. I will only give you examples that are functions, but even if it weren't a function, that's okay. We're really only testing here if it's 1-to-1. So do not worry about the function portion of the question. If we see this 1-to-1, that means we're going to use the horizontal line test, and that is the only one that we will see on the test for this particular unit. Now, on our drill quizzes and on the final, we do need to pay attention to what we're doing here. If we're testing if it's 1-to-1, we're going to use the horizontal line test. If we're testing to see if it's a function, we need to use the vertical line test. Here, though, the word we need to hone in on is 1-to-1. Once again, I am only going to give examples of 1-to-1 graphs that are functions. So anything that we see here where I ask you if it's 1-to-1, it will automatically be a function. In general, that's not true, but for what we will see in this class, that will be true. Okay, so the horizontal line test, what we need to do is to take our graph, draw a horizontal line. If there's a way we can draw a horizontal line that goes through the graph more than once, it is not 1-to-1. So notice this horizontal line goes through the graph exactly once, so that doesn't really tell us much. But notice, say around here, if I draw a horizontal line, it's going to pass through the graph 1, 2, 3 different times. So 3, last I checked, more than 1. So that tells us that this is not 1-to-1. So I'm going to put not 1-to-1. Now a shorthand way of writing 1-to-1 is 1-to-1, just like that. So there's our answer. Not 1-to-1 or simple no would suffice. Either of those would be perfectly fine. So we were able to draw at least one line. One line is all we need to be able to do to show that it is not 1-to-1. To show that it is 1-to-1, I guess technically we don't really show that it is 1-to-1, but in some sense we justify that it is. Looking at the graph, there's no way, we can convince ourselves that there's no way that I can draw a horizontal line that's going to go through this graph more than once. Doesn't matter where I draw it, every horizontal line is going to go through the graph exactly once, exactly once, exactly once. So since every horizontal line goes through our graph exactly once, we can say that this is a 1-to-1 function. Or if you like, a simple yes will suffice here. So example A is not a 1-to-1 function because we were able to find one line that goes through the graph more than once. There are actually a lot of lines that go through it more than once, but we only need to find one of them. Example B is 1-to-1. Every horizontal line that we draw goes through the graph exactly once, so there's nowhere that it goes through the graph 2 or more times, so we're going to say that it is a 1-to-1 function. Okay, so let's look at a little bit more involved, a little bit more difficult problem that we might see from this section on the application portions. So in these problems, instead of being given the graph of the function, we are going to be given just the equation, or just the rule of the function. So we want to actually show that this is a 1-to-1 function. Now I'll help you out. If I ask you to show me that it's a 1-to-1 function, it's a 1-to-1 function. I'm not going to try to throw you off. So to actually prove that something is 1-to-1, we have to use our definition. Recall, we said that f of x is 1-to-1. What that means is if we have the case that the function evaluated at 2 x values gives us the same y value, essentially. What that means is that the 2 x values were actually the same all along. This is exactly what we do to show that it's 1-to-1. We're going to start here. Suppose that we find that the result of this function for 2 x values is the same, and then conclude from that that the x values themselves had to be the same originally. So we can use a and b. So f of a, what I'm going to do is I'm just going to replace my x's with a's. So I have a plus 1 over a minus 2. And I suppose that they equal f of b. So I just replace my x's with b. b plus 1 over b minus 2. So we're going to manipulate this algebraically using just our regular rules of algebra, simplifying equations. Basically, it's going to wind up being not quite a linear equation at first, but very, very quickly it will turn into a linear equation. We will always be able to get to the point A equals B. For these problems, the ones that I will give you, we're going to be able to conclude that A equals B. So even if it looks nasty, hold on, don't freak out too much. Freaking out a little bit's okay, that's kind of expected. But don't just be completely heartbroken here. We're going to be just fine. So I don't know about you, but I've just been trained. Whenever I see fraction equals a fraction, it doesn't matter what I'm doing. I could be playing tennis or something. I've got to cross multiply. So I'm going to write A plus 1 times B minus 2. I've multiplied top and bottom here, equals B plus 1 times A minus 2. So just cross multiplied. Product of these two equals the product of these two. So this looks unpleasant, but let's go ahead and multiply everything out and see that actually once the dust settles, it's not too bad. So let's FOIL out both sides. Notice that we won't get the exact same thing on both sides. We have A plus 1 here, B plus 1 here. So they won't be the exact same, but they will look awfully similar. So A times B is AB. A times negative 2 is minus 2A. 1 times B is plus B. And 1 times negative 2 is minus 2. Similarly, on the right-hand side, we get AB minus 2B plus A minus 2. Now, looking at this equation, we want to look out for things that we have on both sides of the equation. So we have an AB here on both sides and a minus 2 on both sides. So we know that we can get rid of these guys if we subtract AB from both sides and add 2 to both sides. So once we do that, we're left with just terms of A and B by themselves. So we have negative 2A plus B on the left-hand side, negative 2B plus A on the right-hand side. So we want to treat this more or less like a linear equation now. We want to get each variable by itself on one side of the equation. So I like dealing with positive numbers, so I'm going to add 2A to both sides and 2B to both sides. So I'm going to add 2A here and here. And I'll also add 2B to both sides. So that gives me 3B equals 3A. So if I divide both sides by 3, I wind up with B equals A. So our answer here, this is not our final answer right here. Our answer is actually this whole process from here all the way down to here. This is your answer. So don't box in anything, but make sure that your work is fairly clear. I know I've got pretty crummy handwriting, but as long as it's not worse than mine, you're going to be just fine. But do present this in an orderly fashion. From this step we go here, from here we go here, here to here, here to here, and so forth. I am not a big stickler about you showing me we subtract AB, add 2, add 2. Since we are doing simple algebra here, I am not going to be picky if you do not show these steps. If you just hopped from this line right here to this line right here, that's a simple enough step that I understand what's going on. So you don't need to do that. I've shown it here just so that the presentation is crystal clear. Similarly, going from this line to this line, you don't need to show you added 2A to both sides, added 2B to both sides. But do present this in an orderly fashion, present it linearly, don't do a couple steps here, then hop over here, then hop over here. Your presentation for this problem is very important. So do not expect to see anything really any more difficult than this. This is the hardest type of question that I would ask you to do. Even if it doesn't look like this, the process will be exactly the same. Start here, f of a equals f of b, and just manipulate it algebraically until you get to this point here, b equals a, or a equals b. You will be able to get to this point. I will only give you problems that are one-to-one.